Hello, my name is Isaac, and this is my Lab 3 magnetic field of a bar magnet. In this lab, we wanted to utilize equations from the Biot-Savart law to predict measurements of distance dependence of a magnetic field. We also wanted to employ a small bar magnet and a magnetometer to directly measure the distance dependence of that resulting magnetic field. Utilizing a computational model with GlowScript, we compared both our theoretical and calculated values. The brief results of this lab were, we found a magnitude of the magnetic dipole moment to be 2.82 ampere meter squared. We also found the value of n to be equal to negative 2.8378 and the value of k to be 5.64 times 10 to the negative 7. The main fundamental principles and models that we'll be using in this lab consist of the Biot-Savart law, so we can calculate the magnetic field of a dipole, and the distance dependence formulas that were given to us, used to help derive k and n. The assumptions that we brought into this lab was that the magnetometer app that we used accurately described each of the axes, so the x-axis, the y-axis, and the z-axis, and that the bar magnet in this lab acted as a magnetic dipole, which allowed us to use the Biot-Savart law. In this experiment, our system consisted of a bar magnet shown as the gray box on the left, while the surrounding consisted of everything else, which was the ruler and the phone. For this lab, we utilized a magnetometer app to accurately locate the position of the phone's magnetometer, marked by this yellow tape, and the magnetometer was then used to determine the distance dependence at various different lengths. From this lab, I made two different observations. One, when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. In this lab, I recorded multiple distances between the magnet and the magnetometer on my phone that produces a magnitude of 20, 70, 120, 170, and 220 microteslas respectively, shown on the table to the right. Using the data from the previous slide, I created a linear depiction of our data, shown with this line over here. As you can see, the line has a slope of negative 2.8378, similar to our n value, and an intercept of negative 14.388. And I also included the measurements of an off-axis magnetic field shown in the table below. Here are my calculations for each value. From the equation given to us in the lab and the graph of the line that I plotted before, we can see that I determined the n value to be equal to the slope, while the value of natural log of k was equal to the intercept of the graph. Using that value of natural log of k, we were able to raise it with a natural base to find the value of k, which we found to be 5.64 times 10 to the negative 7. And over here is the slope of our line. Since we assumed the bar magnet in this experiment to be a dipole, we were able to utilize the Biot-Savart law and the equation for a B field of a dipole that is parallel. We were also able to use the distance dependence formula given to us from the lab. By setting both formulas equal to each other, we were able to solve for the magnetic dipole moment, mu. And over here you can see I set two equations equal to each other. I solved for mu, which I found to be 2.82 amperes meter squared. In these lines of code, we are using the formula for calculating the magnetic field of a dipole, or the bar magnet in this situation. And over here I'm just scaling our arrows to see in our force diagram. In these lines of code above, we are declaring the observation locations for our graph. Down here, we are declaring arrows and lines to depict in our force diagram. In these lines of code, I am declaring the arrows that represent the magnetic field perpendicular to our axis. In these final few lines of code, I am declaring the arrow to represent our off-axis magnetic field 45 degrees from the axis. Let's compare our fields along the 45-degree axis. From our measured value we got from our magnetometer and our ruler, I found a value of 4.808 times 10 to the negative 5 Tesla. However, our computed model in GlowScript found a value of 2.888 times 10 to the negative 5 Tesla. There was almost a 60% difference between the two values. Possible sources of error in our lab could stem from human error and imprecision when locating the magnetometer on my phone, inconsistencies in reading and recording distance data, and magnetic interference from other objects in the room and surrounding environment. For example, a metal pipe in the floor. What if I hadn't oriented my experiment to compensate for a magnetic north? And what if I just laid my meter stick at some random angle with respect to Earth's magnetic field? Well, without compensation for the influence caused by Earth's magnetic north, nearly all values utilized in this lab would have shifted. This would cause a larger deviation between my computed and measured value of the magnetic field along the 45-degree axis. Now, what if I were to stick two identical magnets together end to end and run the same experiment again? Will my measurements be different? Well, since the magnets would essentially combine into a larger and more powerful single magnet, the measurements will be all increased by a certain constant quantity.